Out there, in the silent dark, the universe is throwing a party and you won't believe the guest list. Stars that eat their own planets. Gravitational waves that shake the fabric of reality. Shadows of monsters so vast, they bend light itself. This isn't science fiction. This is Monday in the cosmos. We live on a pale blue dot, in a quiet solar suburb, a placid, stable neighborhood where the sun rises on schedule and the planets keep a polite, predictable distance. It's comfortable, familiar, but if we dare to look up, and I mean really look deep, past the familiar points of light, past the constellations we've named, we find a realm of such sheer mind-bending extremes. It redefines what we think is possible. We're talking about temperatures that make the core of our sun feel chilly. Gravitational forces that can crush a star like a soda can. Energies that dwarf every nuclear weapon ever built, combined in a single instant. This is not a gentle universe. It is a cosmic arena, a grand, brutal, and breathtakingly beautiful stage. Welcome to the greatest show in the universe, a show of creation, destruction, and mystery so deep, they don't just push the boundaries of physics, they laugh and tear right through them. Let's start with a bang. Literally, a supernova. This is how the biggest stars in the universe check out. And trust me, they do not go quietly. No drawn-out retirement, no fading gently into the night. This is a grand, explosive, spectacular exit. Picture a star, not like our humble sun, but a true titan. 20, 50, 100 times more massive. It's lived a fast and furious life, burning through its nuclear fuel in just millions of years, a blink in cosmic time. Deep in its core, it's been forging heavier and heavier elements, like a master smith working its way up the periodic table. Hydrogen to helium, helium to carbon, carbon to oxygen, neon, silicon, all the way to iron. And iron is the cosmic party pooper. Fusing iron doesn't release energy, it consumes it. It's like the star's core suddenly hits the brakes. The outward pressure from nuclear fusion stops. In that instant, the star's own immense gravity, which has been held at bay for millions of years, wins catastrophically. The core collapses. Not in hours or minutes, but in seconds. It's falling at nearly a quarter the speed of light. In less than a heartbeat, a city-sized core collapses into a ball of neutrons just a dozen miles across. The density is insane. A teaspoon of this stuff would weigh as much as a mountain. The outer layers of the star, suddenly with nothing to stand on, come crashing down. They hit this newly formed, impossibly hard neutron core and, boom, a shockwave reverberates outward with the force of a septillion nuclear bombs. The star is utterly obliterated. Now, imagine this. A single star, in that final cataclysmic second of collapse and rebound, releases more energy than our sun will in its entire 10 billion year lifetime. For a few weeks, this one dying star can outshine its entire host galaxy, a collection of hundreds of billions of other stars. It becomes a brilliant, temporary new beacon in the cosmos. It's the single most violent, explosive event in the known universe, bar none. But here's the crazy part, the part that always gets me. This isn't just destruction. This is the ultimate act of cosmic creation, the universe's ultimate recycling program. In that unimaginable furnace of pressure and heat temperatures soaring to billions of degrees in the shockwaves, something miraculous happens. Elements heavier than iron are born. The violent chaos slams atomic nuclei together with such force that they fuse into new exotic materials. Gold, platinum, uranium, silver. Think about that for a second. The carbon in your cells, the very foundation of life. The oxygen you just breathed in, forged in the hearts of earlier, less violent stars. But that gold in your wedding ring, that platinum in a catalytic converter, that was cooked up in the heart of a supernova and blasted across the interstellar void. We are, quite literally, stardust. The calcium in our bones, the iron in our blood that carries that oxygen. All of it was once part of a star that died a spectacular death billions of years ago. The universe recycled the remnants of its dead to make us. That's not poetry, it's astrophysics, and it's mind-blowing. But sometimes, when the absolute biggest of the big stars die, they leave behind something else. Something that doesn't just fade or cool. Something so strange, so powerful, so utterly opposed to our everyday reality that not even light, the fastest thing in the universe, can escape its grip. When the collapsing core is too heavy to become a neutron star, there is no force in nature left to stop it. Behold, the black hole. The universe's ultimate mystery. A place where gravity doesn't just win. It wins completely, absolutely, and forever. The rules of physics as we know them, the ones that built our phones and sent us to the moon, they don't just bend here. They break down. They scream and surrender. Let's get one thing straight from the get-go. A black hole isn't a hole in the sense of an empty pit. It's a place, an object. It has mass. It has spin. It has charge. At its heart lies the singularity, a point of infinite density where all the star's mass has been crushed to zero volume. Our math says it's there, but our physics has a meltdown trying to describe it. Wrapped around this unknowable point is the event horizon. This isn't a physical surface. It's a mathematical boundary, the point of no return. Cross that line, and you're not coming back, ever. Not a message, not a photon, not a desperate plea. You, and all information about you, are removed from our universe. The pull of gravity here is so intense, it creates tidal forces of unimaginable strength. If you were to fall in feet first, the gravity at your feet would be exponentially stronger than at your head. You would be stretched, and stretched, and stretched, and stretched, into a long, thin stream of atoms of process scientists. With that dark, brilliant humor they have, called spaghettification. One moment you're an astronaut, the next you're cosmic pasta. Wild, right? But here's what's really cooking. For decades, black holes were theoretical monsters, the boogeyman of general relativity. Then, we started finding them. Not just the stellar-massed ones from dead stars, but the real kings, supermassive black holes. We now know that almost every big galaxy, including our own Milky Way, has one of these behemoths at its heart. Ours is called Sagittarius A**. It's for a million times the mass of our sun, lurking quietly in the galactic core, 26,000 light-years away. For years, we inferred its presence by watching stars whip around an invisible point at speeds that defied logic. It was the ultimate circumstantial evidence. Then, in 2019, we did the impossible. The Event Horizon Telescope collaboration, a planet-sized network of radio telescopes, gave us the first ever image of a black hole's shadow. Not the black hole itself, but its silhouette against the glowing, superheated gas of its accretion disk. We've taken a picture of nothing, of an absence so profound it warps the very space around it. A picture of the universe's ultimate Kipautzen. It was a triumph of human ingenuity that still gives me chills. But if black holes are, by definition, black holes, how do we see them? How do we study something that actively erases information from our observable universe? We stop looking, and we start listening. A century ago, a clerk in a patent office in Switzerland had a wild idea. Albert Einstein's theory of general relativity proposed that gravity isn't a force pulling through space, but a warp in the very fabric of space-time itself. And he made a crazy prediction. When massive objects accelerate like to black holes dancing a death spiral, they should create ripples in that fabric. Waves of gravity propagating at the speed of light. Gravitational waves. But he thought they'd be so incredibly faint, we'd never detect them. Like trying to hear a whisper in a Category 5 hurricane. For 100 years, it was a beautiful, untestable idea. Then, on September 14, 2015, at 5:51 a.m. Eastern Time, two impossibly sensitive instruments called LIGO, one in Washington State, one in Louisiana, heard it. They detected a vibration in space-time 1,000 times smaller than the width of a proton. The signal matched the prediction perfectly. The chirp of two black holes, each about 30 times the mass of our sun, spinning around each other hundreds of times a second and then merging into one. That sound is the sound of space-time ringing, like a bell struck by a cosmic hammer. It is a completely new way to see the universe. We are no longer just astronomers. We are cosmic listeners. We're using gravity itself as our telescope. And what this new sense is telling us is blowing our minds. We've heard the mergers of neutron stars, events that forge gold and platinum in their violent aftermath. We're tuning into a universe of silent, catastrophic dances happening in the dark. But for all the violence we can now see and hear, there's a far bigger, quieter mystery hiding in plain sight. In fact, it makes up most of everything. We've been studying the universe with the cosmic equivalent of a flashlight, only seeing what it illuminates, completely missing the shape of the room. Alright, buckle up. This is where things get properly weird. We look at a spiral galaxy, a beautiful pinwheel of billions of stars. We do the math. We add up the gravity from all the stars we see, all the glowing gas, all the planets. And it's not enough. Not even close. According to the laws of gravity, with only that visible matter, a galaxy like that should be flying apart. The stars on the outer edges should be moving much slower. But they're not. They're whipping around as if held by the gravity of something else. Something we can't see. That something is dark matter. It's a form of matter that doesn't emit, absorb, or reflect any form of electromagnetic radiation. No light, no radio waves, no X-rays. We can't see it, touch it, or detect it directly with any traditional instrument. It is utterly, perfectly dark. But we know it's there. We feel its gravitational handshake. It's the universe's ghostly scaffolding. It forms vast, invisible halos around galaxies, providing the extra gravitational glue that holds them together. It forms the skeleton upon which the visible universe is built. And get this is the kicker. For every single ounce of normal matter, the stuff that makes up you, me, this planet, every star and galaxy we see, there is 5 times more dark matter out there. Let that ratio sink in. 5 to 1. We, and everything we've ever known through light, are the minority in our own universe. We are the rare, shiny froth on top of a deep, dark, unseen ocean. And if that's not enough to humble you, meet dark matter's even stranger, more dominant cousin. In the late 1990s, two teams of astronomers were doing something extraordinary. They were measuring the distances to extremely far-off supernova to gauge how fast the universe was expanding. The prevailing wisdom was that the expansion, starting from the Big Bang, should be slowing down over time due to the gravitational pull of all the matter in the cosmos. They were dead wrong. What they found won them the Nobel Prize and sent a shockwave through cosmology. The expansion of the universe isn't slowing down. It's speeding up. Something is acting against gravity, pushing galaxies apart faster and faster over time. We call that something dark energy. It's not matter. It's a property of space itself. Empty space, according to our best theories, isn't nothing. It has an inherent energy. And this energy appears to be causing the cosmos to fly apart at an ever-increasing rate. Now, let's put the pieces of this cosmic pie together. This is the modern universe's recipe, and it's the most astonishing fact in all of science. Dark energy, this mysterious repulsive force, makes up about 68% of the total mass energy of the universe. Dark matter, the invisible gravitational glue, makes up about 27%. Everything else, everything we see, know, and love, all the stars, galaxies, planets, nebulae, you, me, every mountain, every ocean, every song, ever written, all of that normal matter and energy is just 5%. 5%. We are floating on a tiny, gleaming island of the known, in a vast, dark, and utterly mysterious ocean that makes up 95% of reality. We have names for it: dark matter, dark energy, but those are just placeholders for our ignorance. They are the labels on the two biggest boxers in the attic of the cosmos, and we have no idea what's inside. While we're trying to figure out the dark stuff, the universe, never one to be upstaged, keeps showing off with its roster of visible, tangible weirdos. Take pulsars. Imagine the crushed core left after a supernova, a neutron star. Now imagine it's the size of Manhattan but with a mass of our sun. A single sugar cube of this material would weigh 1 billion tons here on Earth, as much as a mountain. Now, set it spinning fast. Some of these cosmic cinders spin hundreds of times per second. They have powerful magnetic fields that channel beams of radiation from their poles. As they spin, these beams sweep across space like a lighthouse. From Earth we see a perfectly timed, rapid-fire pulse of radio waves, or X-rays or gamma rays. Tick, 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 tick. They are nature's most perfect, natural clocks, more stable than any atomic clock we can build. They are the dead, spinning hearts of stars, still beating out a rhythm across the light. But pulsars have an evil, far more terrifying twin, the magnetar. Take that insane neutron star density and crank its magnetic field up to 11. We're talking about a field 1 quadrillion times stronger than Earth's 1,000 trillion times. The forces involved are almost incomprehensible. If a magnetar were to magically appear halfway between the Earth and the Moon, about 120,000 miles away, its magnetic field would be strong enough to wipe the magnetic data from every single credit card on the planet. That's just a parlor trick. Get closer, within a few thousand miles, and the field becomes so powerful it starts to affect the very structure of matter. It would warp the electron clouds around atoms, making chemistry as we know it impossible. It would literally rip you apart, atom by atom, pulling the molecules of your body into distorted, useless shapes. These objects occasionally suffer starquakes, cracks in their impossibly hard surfaces that release bursts of gamma rays so powerful they can be detected from clear across the galaxy and briefly outshine every other gamma ray source in the sky. They are, without a doubt, the most terrifyingly violent objects in our galactic neighborhood. So, faced with a universe of such epic violence and profound mystery, what's next? How do we, with our 3-pound brains and fragile bodies, even begin to understand a reality this bizarre, this extreme, this big? We get clever. We build new eyes, new ears, and new minds to help us. The James Webb Space Telescope is our new infrared time machine. Orbiting 1 million miles from Earth, it peers through cosmic dust to see the first galaxies being born, just a few 100 million years after the Big Bang. It's analyzing the atmospheres of distant exoplanets, looking for the chemical signatures of water, methane, even potential biosignatures. It's staring into stellar nurseries, watching solar systems like our own take shape in real time. It is, quite simply, rewriting the first chapters of our cosmic history book. On a mountaintop in the clear, dry air of Chile, a different kind of machine is about to come online, the Vera C. Rubin Observatory. Its job isn't to stare deeply at one spot, but to watch everything. Every few nights it'll capture the entire southern sky in breathtaking detail. It'll do this for a decade, creating a cosmic time-lapse movie. It'll find millions of new galaxies, track potentially hazardous asteroids, and here's the cool part, it will catch supernovae in the act, sometimes within hours of their light reaching us. It will be a tidal wave of data, a fire hose of discovery, revealing a dynamic, changing universe that's never still. And to listen deeper, we're taking our gravitational wave detectors to space. The LIGO mission will consist of 3 spacecraft, flying in a perfect triangle millions of miles apart, connected by lasers. This will form an observatory so vast and sensitive it can hear the mergers of supermassive black holes from the dawn of time, the steady hum of countless binary white dwarfs in our galaxy, and perhaps even the faint echo of the universe's birth itself. We are moving from static snapshots to a full sensory 4D experience of the cosmos. We started this journey looking for the most extreme things out there, the biggest explosions, the deepest mysteries, the darkest secrets hidden in the voids between the stars. It's a species of curious tool-making apes who, against all odds, learned to look up, to question the dark, to build stone circles to track the seasons, then telescopes to see the moons of Jupiter, then interferometers to hear the ringing of spacetime itself, to point a camera at the heart of our galaxy and photograph a shadow, to run the numbers, stare at the result, and have the courage to admit, we don't know what 95% of the universe is made of, but we're going to try to find out.